Hi, I'll be handling the topic Unleashing the Power of Rust, building safe, fast, and reliable software for the future. So, Rust is a modern system programming language that is quickly gaining popularity. This due to its ability to build safe, fast, and reliable software. And it achieves this by different methods, and one of them, which is what we'll basically be talking about in this presentation, is the ownership and borrowing system. And we'll also talk about few optimization techniques that Rust has put in place that makes its system and its language so fast. And we'll also discuss some of the applications of Rust. So memory management mastery. So in memory management, we every single program that we write needs a form of memory management because we always tend to allocate memory and deallocate memory as the program progress. And if we do not handle this memory well, we tend to cause things like memory leaks. So now a memory leak in a program occurs when the program unintentionally allocates memory, usually on a heap, during its execution, but fails to release the deallocated or deallocate the that memory properly before the program terminates. And this can cause the allocated memory to stay reserved and unavailable to other parts of the program or other processes. And this would gradually increase and cause memory usage to increase over time. So let's take this example, a C++ example. So what happens here is we allocate memory into the heap here, and what happens when the program ends? Nothing happens to data, and this memory allocated is reserved, and other part of the program, other resources cannot use this memory. Now imagine that we actually wrap line 5 with something like a while true, so it will continue to allocate memory until the program crashes. So a simple solution would just be a system to basically deallocate data before the program terminates, which is what we introduce here on line 6, delete data. But what happens when you unintentionally do not deallocate memory, or the program has been so complex, has been designed to be so complex that it's hard to keep track of allocated memory, and deallocating them becomes an issue. So what happens when memory leaks happens? So these are the consequences. You have reduced available memory, you have slower execution of programs on your laptop or on your system rather. Then you have possible program crashes, resource saturation, and maintenance challenge. In order to address this issue of memory leak, the garbage collector comes to the rescue. The garbage collector basically does the dirty work of memory management. The garbage collector is a component of many programming languages and runtime environment that automates the process of memory management. It basically goes through the program automatically to deallocate objects that are no longer being used. So, but the garbage collector has its own drawbacks. It has a performance overhead, for instance, because you actually need a runtime to be able to continually run the garbage collector, and this causes a performance overhead. And also, we don't know when the garbage collector is going to run. It means it is not so predictable. At any point in time, the garbage collector can run, and is going to put a strain on the resources of the program itself, and is going to take more resources than required at that point, and basically halting the program for a few microseconds. So which means using a language that has a garbage collector is not ideal for use cases where we need a very low latency in the program execution itself, because we don't know exactly when it will happen, and if it happens when we need a response, it can cause the metric of the program itself to fail. So in those set of situations like game development, for instance, we basically want to use languages like C++ that we can handle the memory ourselves and deallocate them. But because of the drawbacks of both manually handling memory and using the garbage collector, then Rust came in with its own unique approach to memory management. And it does this without using a garbage collector, and you don't have to manually deallocate memory, although it gives you the chance to be able to do it yourself if you want to. Okay, so it now begs the question, how does Rust handle memory management, since these are the two basic ways that we know to efficiently manage memory? So it does this through a system of ownership and borrowing, and lifetimes and ownership transfers and moves. So we'll basically be talking about this system in this presentation. So take this example. So we'll use a few examples to demonstrate exactly how Rust handles its memory. So if you take this example, it's a program that is supposed to run, but then this is what happens. If we take a function, take ownership for instance, that has an argument s, what take ownership wants to do is it wants to containerize its memory, and basically when it's going out of scope, it will say, okay, I have a few objects that I own, and since I know they will not be used in any other place, deallocate them. So the compiler will include something like drop, like a function at the end of the program, or calls drop on the own variables basically. So by the time we finish running take ownership, we are very sure that on line 10 s is dropped, it is deallocated. But what happens if you try to access that memory after them, that's after line 3? So on line 3 you call take ownership, and anything you pass into this function take ownership is dropped here, because it is basically moved. That's this string is basically moved into this place, and it means that if we allow this program to run, we will have a null pointer issue in this that's in this particular place. So this is one of the ways that Rust handles it. So to recap again, is a simple philosophy. Any data I own, the moment I'm going out of scope, I'm going to destroy them basically, and deallocate the memory. So that's basically it. So the compiler really helps to enforce these rules and make sure we don't have things like null pointer exception, which we would have had here. And this is the error that would have gotten from this program if we had tried to run it. We'll have this move occurs because string has a type string which does not implement copy trait, and the value is basically moved into this take ownership, and it doesn't exist in the scope of, it does not leave enough to reach line 4 basically. Okay, so what if we want to use the value returned from take ownership? Okay, so we can basically assign that value to another variable which leaves long enough to reach here. But it begs the question, okay, what if we still want to use string after we run take ownership? So what we'll do, instead of moving string into take ownership, what we'll do is that we'll say, okay, since you would go out of scope and you are going to destroy, that's the main function will basically tell take ownership that since take ownership you are going to go out of scope, and when you do go out of scope, you are going to drop anything I give onto you, anything I give you. Why not I lend you a reference instead? And take ownership can borrow a reference, and it knows that okay, it doesn't own the reference and it doesn't destroy it by the end of its own cycle. Okay, so let's take an example which is using this calculate length. Okay, so this is the example which is basically like the previous one, and we still have this issue of string not living long enough to reach line 5. Okay, so the philosophy here is line 2 we create string, line 3 we move string into calculate length. When calculate length reaches line 11, it goes out of scope and it calls drop on S. So since you've moved string into this place, it owns S and it drops it and basically deallocate the memory. So we don't have string again. It does not leave to see line 4. So by the time you get to line 5 and you're trying to access it, the compiler is going to complain and tell you the value has already been moved. So basically to fix this, we can say, okay, calculate length. Can say that, okay, instead of me calculate length owning any value given to me, why not I borrow the value or the reference to that value instead. So what happens here is calculate length to say, okay, I just want something borrowed and I'm going to have I'm going to use it for a particular thing, and when I'm done, I'm not going to deallocate it. So basically by line 12, when calculate length runs by line 12, it checks for everything it owns. It does not own S, it is a borrowed value, so it does not deallocate it. And we know in the main function, if that is the philosophy and if that is how calculate length is declared, it means that after line 4, after line 3, we can still be sure that this string that is declared on line 2 is not deallocated. So basically, it creates a reference and passes it to calculate length, and calculate length doesn't own it, so it does not deallocate it, and which means that the string itself can still be used in line 5. It still lives long enough to be able to get to line 5. So it's a very simple principle which allows the Rust system to be able to manage the memory in a tight knit manner and not allow any memory to leak. Okay, what if you want to handle a scenario that is multi-threaded, for instance? Okay, but before we get to that, let's first talk about like different ways we can handle this. For instance, if you actually want to modify in some cases, and in some other cases if you don't want to modify. Okay, so this is a TypeScript file. It basically has a class of user that has a first name, last name, and an age, and also a constructor that takes in these arguments, and a function that which is set age, and the set age just changes the value of age. That's all. So in our main function, we create a variable online 18 named user, and we have a function that is called cannot modify user. So we want this cannot modify user to work in such a way that it just uses the value from user, but it does not modify the user object itself. Okay, I want a way to be able to enforce this and not be able to change the value of user by mistake. But what if I do user.setAge in cannot modify user? It changes the value of the user object itself. It changes the value, and that is not what we want. Okay, so to fix this issue in TypeScript, we can basically do something like object.freeze, and it freezes the values of user, and you cannot change it after this point. And this fixes the issue, because when we try to run this program, when it gets to line 27, it throws an error, which is what we want, that we cannot assign a value to a read property. But then we are changing the behavior of user because we want a function not to modify it. What if we want another function to modify it? Okay, so let's explore that direction. So if we have another function which is can modify user now, for instance, and we now call user.setAge44, this function does not work because we are using object.freeze. Yeah, so it makes it read only. And this behavior is something that we should be able to write out in a language and not do it unintentionally. Because if we remove this object.freeze, we can mistakenly modify user inside the cannot modify user function, which is not what we want. Okay, so this is Rust's approach to this. So we have basically the same code. We have struct user, which has the first name, last name, and age, and it has a method which is set age. So on line 15 we create a function user, and it is made mutable because on line 22 we can modify it. So when we create a function cannot modify from line 27 to 29, that takes in a reference to user. So basically it does not, it just borrows user, and anything it does not modify user. Okay, this function, and if we try to modify user inside this function, the program does not compile. The compiler would complain and basically scream at us. So if we try to do that, that inside this cannot modify function, and we do user.setAge, it does not allow us to modify it because we are passing a non-mutable function, a reference to cannot modify, which is the behavior we want. And yes, it's acting exactly the way we want. And the same way, in this can modify user, we can use this and mute user, and we can basically specify that this can modify function is telling the main function that, okay, if you are passing me a value, I am going to be able to modify it. So that's basically what is happening here, and we're able to modify. So we can have this implementation and also be able to efficiently predict how the behavior is going to, the behavior of the program is going to be without seeing the implementation of cannot modify and can modify. So if we have this type definition, that imagine we don't know what is happening inside there, we can be very sure that when we call cannot modify, the user object is not modified, and when we call can modify, because it's saying, okay, I would be able to mute it by borrowing a mutable reference, it's saying that, okay, it will be able to modify, which is very different from the TypeScript version, which would not allow us to do that, and the program is more unpredictable. Okay, so another scenario where we typically want to use another scenario where you would want to imagine how memory is being passed is in multi-threaded programs, and many programs are multi-threaded. So if we take this example, for instance, we will basically have the same thing for the struct and the method. So on line 17 we are creating a new user, and on line 23 we are basically creating a new thread. We are spawning a new thread and making sure it runs on line 27. Another thing to note is in Rust, threads are lazy, so until you hold them, they are not going to run. So the thread actually starts running on line 27. So what happens is this user variable is moved into the scope, and we can tell the compiler to move this variable into the scope by specifying this move keyword. Basically, this program would run as we want, it will run so fine. So when it gets to line 27, it will run this, and it will basically move user, and when it's done with this, that when it gets to line 25, it deallocates user. Perfect. But what happens if we have more than one thread? So we have thread 1, thread 2. So let's just move threads. Okay, on line 31 we are saying, okay, run the first thread. So we'll come to this thread and we say we move user into this thread. When we get to line 25, the thread sees user as a value that it owns, so it deallocates it. So by the time we come back to line 32 to run this second thread, the user variable does not exist anymore because it has already been deallocated by handle by the first thread, which is not what we want. But the compiler also complains and tells us we need to that's the value has already been moved into this first thread's scope, so we need a different way to handle this. So one of the easiest way to handle this is using an arc, which is an atomically reference counting struct. Basically, so it's wrapped around the user, and you can create different clones of that, which you can now move into different contexts. So the arc allows you to be able to create multiple ownership of a particular object. So if I wrap an arc over this user, I can clone it, then move the clone value into the first thread, then clone the second one, then move the second value into the second thread, basically. And the program runs as we expect. Okay, so let's check some optimization techniques by by the Rust system. So Rust is a programming language that emphasizes and safety, performance, and concurrency. It provides a variety of optimization techniques to help developers write efficient code without sacrificing safety. And one thing you should notice, many of these optimization you do not need to write yourself. Okay, so let's take the first one, which is the zero cost abstraction. So the zero cost abstraction in Rust, that's the when Rust gives us a high level abstraction, they do it in such a way that it does not incur any runtime overhead. For instance, the ownership and borrowing system in Rust, the ownership and borrowing system in Rust does not require us to be able to drop the value, like free a particular memory by ourselves, but it basically abstracts the manual memory management by itself, and it does it in such a way that does not incur any runtime overhead by using a garbage collector, for instance. Okay, so another example of zero cost abstraction is when you are using iterators. Iterators in Rust have zero cost abstraction. If you compare iterators in Rust to something like iterators in C Sharp or iterators in Java, the iterators in C Sharp and Java, they are typically slower than you writing out the iterator yourself. So for instance, if you have an array and you use an iterator to map the array into something else, the execution speed in both C Sharp and Java is much lesser than if you actually write out your loop manually and do your mapping yourself. But in Rust, the using the iterator would be faster than writing it out yourself. Basically, Rust ensures that every abstraction, every high level abstraction that is being given to the programmer is optimized in such a way that if the programmer hand writes the logic, it will not be as fast or as optimized as the abstraction that they are giving. So another way to suggest to the compiler for an optimization is inline function. So an inline attribute in Rust is a compiler directive that tells the compiler to inline a function at the call site. This means that the compiler will copy the body of the function into the caller's code instead of calling the function as a separate entity. This can improve performance by eliminating the overhead of the function calls such as stack, frame, setup, and teardown. The compiler will not always inline a function that is marked with the inline attribute. The compiler will make a decision based on the number of factors, such as the size of the function, the optimization level, and the target architecture. Okay, so this is how to use the inline attributes declarative in Rust. So you just put the inline like it's done on line 1 here, and the compiler knows what to do. It basically copies the implementation and paste them here itself. So doing that would remove the overhead of calling the function itself. As basically using the inline directive is the best places to use them is when you have the ideal case would be when you have smaller functions that are called multiple times or they are called frequently in your program. So you can use the inline declaration attributes on your function. Okay, so another optimization technique is using the constant propagation. So the constant propagation in Rust is basically the compiler replacing expression. It will basically evaluate an expression that it's that would always evaluate into a constant and replacing it with the evaluated value at the call of that's at the point of evaluation. So what it basically does is it will improve performance by eliminating the need to evaluate the expression at runtime. So the Rust compiler can propagate constants through expression in a number of ways. For example, if an expression contains a variable that has been assigned a constant value, the compiler can replace the variable with its value. The compiler can also propagate through arithmetic operations such as addition and multiplication. For instance, using in this program, if you use a const pi, you are telling the compiler that okay, this is a constant value, and it will basically propagate this value into this place. So the compiler is also smart enough to see that okay, radius is not has not been reassigned, and has not the value of radius has not changed. So the compiler would do 2 times 5 times the value of pi and replace this expression with that value as compile time. And what that does is it would eliminate the need for evaluating this at runtime. Okay, so using the static variable, using the static variable is very similar to using the const, but the major difference, or one of the biggest difference, is that when you're using the static variable, it basically creates a value on the heap and gives it a lifetime of static, which means it lives as long as the program lives. It deallocates this memory when the program terminates basically. And the compiler can also use this value for constant propagation, as we've discussed in the previous slide. um okay, by utilizing constant and static variable, Rust compiler can perform various optimization including constant propagation, which can lead to more efficient generated code. This optimization can eliminate unnecessary runtime calculations and improve the overall performance of Rust programs. Okay, some usage of Rust. We see the usage of Rust in operating system, and yes, is not a surprising usage, because one of the biggest issues with operating system is memory leaks, and there are some notable projects that are already using Rust for the operating system, something like Redux OS and Talk OS, and even Microsoft is also rewriting the core Windows libraries in Rust. And we have servers developers. So because of the advantages that Rust brings to the table, we can also use it on servers. And we already have projects like Actix and Rocket that provides framework that leverages Rust and concurrency model and memory safety to develop robust web application. Then we have other applications of Rust, something like in databases, game development, embedded system, blockchain, and cryptocurrency. So we also have in networking, we you can use Rust. So basically, for a recap, is that most of the optimization that I want to do in Rust has already been done by the developers of Rust themselves. Although there are some instances that we can optimize our code and um to also run like very fast or to improve the performance. But then Rust has also done a lot of optimization, and we not even talk about things like unwrapping of loops and some other optimization technique that Rust use. So thank you for listening and tuning in to this talk. And also remember, with great power comes great responsibility. Thank you.